I normally ask people to make little tags and keep them in front of themselves so I know their names. But considering that this classroom doesn't have desks, we cannot do that. So if I point to you, I expect you to identify yourself, introduce yourself. Not just today, but for the next several classes, because of the probability of 1, I'm going to forget everybody's name as soon as you tell me, right? I have to keep practicing it till I begin remembering your names. I expect all of you to know who I am. My name must be familiar. Me and some of the TAs. Do we have any of the TAs over here? Wendy and one other person. The only person in class who is allowed to keep their laptop open currently, the only people are the TAs, and for today's volunteers, Vedant out there, who's going to be following the class, following Piazza in order to forward any questions that might be posed on the streaming by people who are following the video stream online. All right? So let's begin. I assume all of you have actually looked at the logistics lecture, but I'm going to go over some of it anyways. But even before that, as a quick intro, here's something we're all familiar with. You've probably seen this slide before already. Neural networks are pretty much taking over every aspect of AI these days. In most problems that you can think of, the state of the art currently has been established by neural networks. So here are some historical highlights. Speech recognition. We've been trying to perform speech recognition, automatic speech recognition, since the 50s, or maybe even earlier. And the performance of automatic speech recognition systems until about 2015 left a lot to be desired. Although we did have things like Siri, which were pretending to perform speech recognition, more often than not, they were more useful for humorous purposes than for actually for anything useful. But then something happened in 2016. Microsoft came up with this, note the date, October 2016. So we had this article which said Microsoft AI beats humans at speech recognition. This was on a specific task. It did not generalize. But it's been 3 years since then, and guess what? Things have gotten exponentially better. These days, an automatic speech recognition system can outperform you on most tasks. Machine translation. Observe the date over here. This is there a date? There must be a date. November 15th, 2016. These things are coming really close together, right? So if you used Google Translate in October of 2016, you translated something from English to Spanish, took the Spanish string that came out and translated it back to English. What came out would have no relation to what went in. It was it used to be very humorous. In fact, we used it for playing jokes. And then something crazy happened in November 2016. One fine day, you just woke up, you tried Google Translate, and voila, the thing actually worked. It gave you useful translations. These days, you can use machine translation systems. Do you mind shutting your laptop? Yeah. So these days, you can use online machine translation systems, and they do an excellent job. In fact, very often, they outperform human translators. So what happened? In November 2016, Google switched from using their statistical machine translation systems to something based on neural networks. Similarly with image segmentation. This is a picture that I got from the web. Obviously, everything you get from the web is true, so this is correct, right? Now, trying to identify all the objects in an image, to even segment out all the objects in an image was incredibly hard just a few years ago. Few as in 3 years ago. And trying to identify every one of these objects on top of segmenting them out was something quite impossible. But today, something like this, where you have an automated system that not only segments out pretty much every object in the scene, but can assign a tag to it. These things exist, and they are powered by neural networks. Here's a beautiful little demo that I got. I don't know if this will work. Again, I got it from the web, so it must be true. But this is powered by neural networks. You can see a system that's actually detecting and tracking automobiles on the street as they drive down live. And not only is it finding the automobiles, it's actually telling you which model it is. Pretty amazing, huh? Then what about games? How many of you know where the world's first chess game that beat a human grandmaster was built? Yes?
It was built by IBM back in
Anybody else? Down the hallway, Wien Hall, right? So this was, again, this was the PhD thesis by a guy called Thomas Anantharaman, who was actually not working on chess at all. He was trying to build processors for dynamic programming. He had to try it on something, so he decided to try it on chess. And the next thing he knew, he had a chess game that beat a grandmaster. It was called Deep Thought. Then he went to IBM, and then it became Deep Blue. And Deep Blue is the one that actually beat Garry Kasparov. So again, for a very long time, the notion of what it meant to be intelligent, what it meant to be smart, was identified by these really smart cerebral games like chess. And it was assumed that computers could never really beat the best humans at chess. And well, along came 1995, and of course you had AI systems beating pretty much everybody all the time. But then there was a tougher game, Go. And Go is exponentially harder than chess. In a typical chess game, there are 10 raised to about 120 possible states, and I think Go has 10 raised to 200. So the state space is much larger. It was expected that a machine could never really learn to explore that kind of state space. You need human smarts. And then in around 2016, you had AlphaGo, which beat the human champion, Lee Sedol, at Go for the first time. And those charts over there now tell you AlphaGo required a lot of training. It had to be taught how to beat the human, but this was a neural network-based system. These days, you can pick up AlphaZero, and AlphaZero will start from scratch without knowing the rules of the game. And in a few hours, it will teach itself to beat the best game, automatic game out there. It can beat AlphaGo. It can beat AlphaGo's successors, which are even better than AlphaGo. And again, this is powered by neural nets. So you see where this is going, pretty much everything. This is an old paper. These are all images, and you can see captions underneath the images. Those captions are provided by neural networks. And you can see they're pretty amazing, right? Girl in pink dress is jumping in the air. That's accurate, and that has been generated by a network. Black and white dog jumps over a bar. Man in blue wetsuit is surfing on a wave. I mean, pretty accurate. And all of these have been done by neural networks. So, point being that these systems are almost magic on a variety of problems, including the ones you've seen, down to astronomy, healthcare, the finance market. Neural networks are the way to go. I like to joke that it's a common fallacy amongst people that you cannot rub your stomach and pat your head at the same time. But this is powered by a neural network, is just in his head. Anyway, the biggest factor here is 4 years ago, if you knew about how to code a neural network, you were it was a hot item on your resume, right? These days, if you don't know how to code a neural network and to make it really sing, then you're not going to find a job. So it's gone from being a plus to being essential. You better be good at this, right? So what are the objectives of our course? We're going to try to understand neural networks. We're going to comprehend the models that do all of the previous tasks. If they look like magic now, they will not look like magic 3 months from now. And you may even be able to build some of these. You will be familiar with a lot of the terminology. There's a link over here on the slides. The slides are up on the course page. And this blog maintains a list of all of the latest neural network architectures. I expect that by the end of the course, you will be able to understand what each of those architectures is and maybe even implement them. And basically, the idea is that by the end of the course, you will be fearlessly able to design, build, and train networks for various fairly complex tasks. Again, keep in mind that this course title is Intro to Deep Learning. So it's an introductory course, but don't let the name fool you. It's an introductory course only at the beginning. When the course ends, you would have gotten in so deep you won't believe it. By the end of the course, it will be quite amazing to you how far you have come. And at that point, the course will not be an introductory course anymore. You will actually be not an expert, but fairly close to one. I'm the instructor. That's my email, bhiksha@cs. My phone number is 9826. I have not actually assigned listed office hours for myself on the website because I tend to be extremely indisciplined. And part of this indiscipline means that if you walk into my office, I'll talk to you. I'm always accessible. If there are people waiting in my office, you just walk in and you sit down. Very often my room is so packed that you have to sit on the floor. Just wait. I'll get to you, right? We have an army of TAs, at least 2 of who are here. I see Wendy. I just saw Parth come in. Parth. So we have 15 TAs scattered across 3 campuses. And these are your supermen and superwomen who are actually going to help you through the course. Most of them have been through the course, and all of them have been through an equivalent of this course. They know their stuff, so they'll be able to help you. Office hours, the TA office hours are going to be on the web page. Yeah, here they are, right? TA office hours will be on the web page. The course page, of course, is deeplearning.cs.cmu.edu. So it's going to be easy for you to actually find it, and all information will be on the course page. Most relevant logistics, including the schedule, are going to be on the course page. There's Aishwarya, one of our TAs, has put up a video with the logistics. I assume most of you have seen it. If you have not seen it, I recommend that you actually see it because all the rules for the course are in that video. So you really must see it. The lady over there, do you mind shutting your laptop? There's a strictly closed laptops class, right? And if you have not seen the logistics, this will be maybe new, but hopefully everything that I'm going to say in the next 5 minutes is something that you're already familiar with. We have in-class sections. This class has several sections. This classroom, of course. Typically, the classroom tends to be much larger than this, but I chose a smaller classroom because one of the magical things about the fall semester is that as the semester progresses, the days get shorter and it gets colder. We also have online sections. All the lectures are being streamed. The streaming link is on the course page. The lectures are also recorded. These videos are going to be on MediaTek's Panopto, and they will also be on YouTube, which means that you can watch these videos offline. Now, while I do not recommend it, in fact, I strongly do not recommend it. I recommend that you come to class every single class. What I expect is that most of you are going to ignore my recommendation. So by the time it's November, nobody wants to wake up at 8 a.m. So you'll maybe crawl out of bed at 8:45. I'm imagining this, and then roll to your computer and watch the video. That's not what happens. You wake up at 10 o'clock, say, oops, we had a class, then go to the web page and try to figure out if the video is on the web page. And then say, okay, it's too long. You play it at 4x speed. I'm squeaking. And then you go and answer the quiz and you fail your quiz. Because if you don't actually watch the videos, you will not be able to pass the quizzes. So it's important that you actually watch the lectures, even if you think you know the topic. We have 13 recitations. We may have a 14th if required. There's a tentative list of all the topics on the course page. I'm saying tentative because we tend to be nimble on our feet. Depending on how the course is currently progressing, we might change the schedule to add or subtract recitations. These will cover implementation details and basic exercises. It is important that you actually attend all of these recitations. Again, the idea here is that you become near experts on the topic, and if you miss the recitations, that's not going to happen, right? The topic list is on the course schedule. Quizzes, we have 14 quizzes, one every week. We'll retain the best 12 quizzes. And so which means that if you get, now each of these quizzes is a multiple choice test that'll be up on Canvas. And if you manage to score perfectly on the first 12, you don't need to take the last 2, but nobody scores perfectly on the first 12. There are 4 homeworks. Each of these has 2 parts. One is on AutoLab, the other is on Kaggle. You compete with each other on Kaggle, which means that don't cheat. If you help your friend cheat, your grade goes down, because we're going to be we're competing. You're competing, remember? So we recommend collaboration, we recommend discussion, but at the end of the day, we want everybody to do their own stuff. So it's perfectly okay to share all kinds of information. What it's not okay to share is work. You have to do it yourself, right? And we've put up some practice homeworks over summer. Hopefully at least some of you have tried those. If you haven't, I recommend that you do because it'll get you warmed up, right? And hopefully you've also seen Recitation 0, which is in 3 parts, the last of which went up only yesterday. If you haven't, please go over all 3 because this will really, really help. Now, the slides that I'm showing in class are not the entire set. The actual slide deck has many more slides, more often than not. So even after class, you must download the slides and go over the slides to cover the entire material. Now I'm very cunning and evil. So most of the questions in the quizzes will be from the slides that I don't present in class. So, well, not all, because I want you to be in class. So some of those questions will be on stuff that I say in class, but it's not on the slides. Right. And here's my chicken slide. You've all probably seen it. The course is a lot of work. Just to emphasize, it's a lot of work, right? In fact, it's a lot of work. It's not for chicken, right? That's how tough it is. We pile it on with the best of intentions. You'll hate me 2 months from now. You'll love me 4 months from now. Simply because if you stay with it, at the end of the course, you're going to be really happy with where you are. The evaluation is based on mastery. We have timelines, we have deadlines, like every other course, but timelines and deadlines are for administrative purposes. If you don't get things done on time, I will not be able to score you and grade you before the semester ends. So nobody will actually pass the course. So I recommend that you actually follow the timelines as strictly as you can. But our objective is to make sure that you're actually really good at the course. Do you mind switching off your phone? You in the middle? Yeah. Thank you. I'm going to pick on you if you do this in class. Just remember this, right? Last semester, I think half the class got some version of an A, maybe slightly more than half the class got some version of an A. Nobody got a free grade. It was hard. Every one of the students who got an A deserved it. My point in saying that over half the class got some version of an A is to tell you that it's possible, provided you put in the effort, and I expect that you will. And if you have any questions, please post on Piazza. Piazza is monitored pretty continuously over the past 3 semesters. Our TAs, like I've told you, they're supermen and superwomen. They've done a wonderful job. We've maintained an average response time of less than 12 minutes over 4 semesters. TAs have won awards for their work in this course. So even more than me or the content material of the course, our TAs are famous, which means use Piazza freely, you can expect to get a response, right? And before I close the intro, I'd like to close with this little quote from Rosenblatt's book in 1962. He actually quotes this book called Perception and the Representative Design of Psychological Experiments by Egon Brunswick, which tries to define perception, which is at least part of what we're going to be looking at. And can anybody read it? It's really long and complex. Perception then emerges as that relatively primitive, partly autonomous, institutionalized, ratiomorphic subsystem of cognition which achieves prompt and richly detailed blah, 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 blah. And I think the New Yorker actually summarized it really nicely. It says that's a simplification. Perception is standing on the sidewalk watching the girls go by. Anyway, that was just the introduction. We're going to start off with the topic for the class, but any questions? On Piazza? No? Anybody? Yeah. The mic, there is no mic in the class, so you're asking me to yell louder. Okay, I'm happy to do that. This thing is only going over the streaming link. So yeah, I'll speak louder. Can you hear me? Yes. Perfect, okay. Anything else? All right. So what we've said so far is that there's this magical box called a neural network, which does all kinds of amazing things. It can recognize speech, it can play games, it can assign captions to images. What really is happening in each of these cases? There's a box, something goes in, something comes out. A voice signal goes in, the transcription comes out. An image goes in, the caption comes out. The current game state goes in, the next game state comes out. So what we are really trying to do is to figure out what's in these boxes. What is really in these boxes? Now, before we begin, the first thing we have to realize that all of these tasks are fundamentally human tasks. Playing clever games, very human. Speaking and recognizing speech, very human. Assigning captions to images, very human. These are all human tasks that are powered by the human brain. So maybe we should begin by, now here's one common architecture, the brain, which performs this magical diversity of tasks. So if we want to have some kind of a common framework which can do all of these things, maybe we should begin by trying to understand what the brain really does. Or even before that, what does it mean? What does cognition mean? How do we actually, how does cognition work? Now, any of you know what the statue is? I've been very helpful. I put a caption on the slide. This is Augustin Rodin's The Thinker. And the guy, that statue, that represents a specific character. Anyone know who that is? That's Dante Alighieri, right? The Divine Comedy. Okay. So here's what human cognition can do. Human cognition, humans can learn. Humans can solve problems. They can recognize patterns. They can create. You can be having a shower and you can think and you can come up with ideas completely randomly. You can cogitate. So these are all these beautiful aspects of cognition that are worthy of emulation. This is, in fact, when we begin speaking of AI, these are the kinds of things we would like our system to do, right? So this is definitely worthy of emulation. But for this, first we've got to understand how humans work. And the problem, of course, is the age-old problem, which is if the brain was simple enough to be understood, we'd be too simple to understand it. It's a very beautiful quote by Marvin Minsky. But that doesn't stop us from trying. So we've been trying for hundreds, no, thousands of years. It turns out the earliest attempts at trying to understand how cognition works goes back to about 600 BC. And it was in around 400 BC that Plato actually came up with the first theories of cognition. He said it's all based on forming associations. He came up with the theory of what was later called associationism, and that was the dominant theory for how cognition worked for over 2,000 years, till well into the early 1900s. There are several famous names associated with it, including Ivan Pavlov, who, of course, ran this famous dog experiment that pretty much everybody has heard of, right? So what is this business of associationism? The concept that they came up with is that our ability to think, our ability to recognize and act on recognitions, to come up with inferences, is based on associations. So here's a simple example. Lightning is usually followed by thunder. So you observe these things happening together, and you form an association between lightning and thunder. Thereafter, if you observe some lightning, you expect to hear thunder. If you hear thunder, you believe lightning must have struck someplace even if you didn't see it. So you've actually formed an association, right? So, and if you think about modern machine learning techniques, this sounds very crude, but pretty much everything that we do is about forming associations. You associate an input to an output. These associations may be arbitrarily complex, but it's still associations. Functions are associations, right? So the idea itself is pretty smart, but then it's still very naive. Just saying you're forming associations doesn't quite explain it. For a start, even with the brain, sure, you have all these associations, but where are they stored? And how? We need to understand that, right? And so let's go back to our favorite exemplar of something that actually does a really good job of intelligence, the human brain. we have to look into the human brain to figure out how these associations are stored, how these inferences are made. And by the mid-1800s, people pretty much understood what the brain was constructed, how the brain was constructed. That's because by that time we had figured out how to build fairly powerful microscopes. You could take slices of the brain, you could look into it, and what they found was that the brain is a mass of neurons. You have many, many, many neurons. How many? We didn't know for a long time. We just knew it had neurons. And these neurons connect to one another. Every neuron is connected to by several neurons. Every neuron connects out to several neurons. So clearly, we have to look at this structure to figure out how the whole mental process works. But just having this structure in mind, knowing this structure doesn't quite help you. You still need a computational model for this. And it turns out that the first computational model for how the brain operates was proposed at this point about 150 years ago in 1873. So the first neural network, artificial neural proposal for an artificial neural network was in 1873 by this guy called Alex Bain, who came up with, who wrote a beautiful book called Mind and Body in 1873, where he proposes this idea. So now, why was this business of trying to figure out how the brain worked so complicated? You had this one small object. It was just one object, but it was performing a plethora of different operations. You had the same circuit doing different things. And it was inconceivable to people early on that you could have one little, can you open the door? Yeah. That you could have one little computational mechanism which would perform different, completely unrelated kinds of computations. And Bain came up with this idea that, it's all in the connections. If you connect these units just right, then they can perform different computations. They can produce different outputs for different inputs. These days, we just take that for granted. But in 1873, this was a revelation. So here is an example of a circuit he came up with. If A and B fire, then X fires. If A and C fire in this figure, Z fires. If B and C fire, Y fires. So it's one common circuit, but depending on what the inputs are, you have different outputs. He actually came up with even more detailed models where he said the strength of the input can modify the output. For example, over here, if the input is relatively weak, then only Y will fire because the input is being added 3 times in Y. But if it's strong, even X will fire. So just the level of the input can change the output. Again, these are things that we just take for granted now, but in 1873 it was pretty remarkable. And the fact that he hypothesized this model meant that he actually had to face a lot of detractors who thought the whole idea was very hokey. And Bain not only came up with the idea that the information is in the connections and how the units are connected, he also came up with hypotheses for how a raw brain could learn to form these connections. So he said when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. He was actually predicting Hebbian learning. We'll see Hebbian learning in a few minutes. So it was a brilliant idea. It was way ahead of its time. And here's a famous quote by Bertrand Russell. The fundamental cause of the trouble is that in the modern world, the stupid are cocksure while the intelligent are full of doubt. So, and this still holds true, right? Now, in 1873, Bain postulated that there must be 1 million neurons and 5 billion connections just so that you can store 200,000 acquisitions, 200,000 of these perceptions or concepts. But then after a while, after 10 years, he realized that if there's a learning process, then there are partially learned concepts, partially learned acquisitions. Where do you store those? And now that's going to need more than 1 million neurons and 5 billion connections. The more he thought about it, the stupider it sounded. And it wasn't all himself. There were a lot of people telling him he was stupid. And so by 1903, he decided he really was stupid. He said, I was wrong. I'm sorry. Please forgive me. And he died. And now, except he was right. So fortunately, the idea stayed, and this idea that that the magic lies in the connections stayed on. This is the so-called connectionist framework, connectionist models for computation. Again, the earliest hypothesis that the brain is a connectionist machine where the information lies in the connections comes from Bain in 1873. There were other reports later on. The idea is that neurons connect to other neurons. The processing capacity of the brain is a function of these connections, and connectionist machines emulate this structure. Now, why was Bain wrong? It turns out that he simply completely underestimated the scale of the brain. Does anybody know how many neurons there are in the brain? Anyone? There are about 80 billion neurons. That's a lot of neurons. How many connections? Anyone? Trillions. So the number of connections in that little thing you got on top of your neck, it has 1 trillion connections and 80 billion neurons. Now imagine building this in silicon. If you are building a little processor with 80 billion units and 1 trillion connections, how much power would it take? Anybody want to guess? You're probably going to have to build your own little, power generator with your own little power station just to power it. But you power that massive computer in your head on a slice of bread. Stop and think about it, right? So that's what Bain completely underestimated. But now we have sort of come around to the idea that connectionist machines are a really good idea. What are connectionist machines? These are networks of processing elements. All world knowledge is stored in the connections between the elements. And connectionist machines differ from your standard computer in your smartphone, in your desktop, in your laptop. What is the architecture of the processor in your laptop? Anybody know? It's the von Neumann architecture. What is that?
You would have a central CPU processor with RAMs and also other connected units.
Anyone else?
For separated computation.
Anyone else who can tell me what a von Neumann architecture is? How many of you are electrical engineers? And how many of you are CS grads? Come on, only 4. What is the rest of you? What is your major? Or do you just not like raising your hands? I think you don't like raising your hands. Okay. Anyway, so here is if you don't answer my questions, I'm going to stick my finger out and point at, say, you, and then you're going to have to answer my question. Just get used to the idea. So here's how the modern computer works. We use something that's called a von Neumann architecture, not quite a von Neumann architecture, but something very similar, which is that the processor is separate from the memory. So you have a processor, you have a memory, and you can store programs and data in the memory. Even within that, you have different designs. The so-called Princeton architecture had one common memory for both the programs and the data. The Harvard architecture, which is more efficient, has a separate memory for programs, separate memory for data. And the machines that we actually use these days are some kind of a hybrid, where within the processor it has a Harvard architecture, so that you have a different segment of memory for the program, a different segment of memory for cache. But then when it goes out to main memory, it's actually the Princeton architecture because it's one common memory where everything is stored. But the point is, this architecture which separates the memory from the processing is what gives you this extremely versatile processor or computer that you currently have, because you can just take the same block, you can change what's in memory, you can get different programs. You can get different kinds of computation. The problem with connectionist machines is that the machine is the memory. The machine is the program. If you have to change the program, you have to change the machine, because the program is in the connections. It's fundamentally different in the way it actually does its operations. So, a quick recap, everything that we've looked at so far. Neural network-based AI has taken over most AI tasks. They originally began as computational models of the brain, or more generally, as models of cognition. The earliest model of cognition was associationism. The more recent model of the brain is connectionist, which is neurons connect to neurons. The workings of the brain are encoded in the connections. And current neural network models are connectionist machines which emulate this architecture. Questions, anybody? Yes.
How do connectionists actually replace association?
So the association, now again, we'll get to that, right? But remember here. Oh, so how, thank you. How do connectionist models actually represent associations? Now, as we will see in the next few minutes, these are actually functions. An association is just a function. You give it an x, it must associate a y with it. And so this connectionist architecture can actually learn these kinds of representations. Hopefully I will answer your question with some more clarity in the next few minutes, right? But let's go back to connectionist machines. This is a network of processing elements. The all world knowledge is stored in the connections between the elements. Now, to understand how these would store associations or how they actually perform computations. Now, what is an association? If X happens, Y must happen. This clearly tells me that there must be some connection between X and Y, and triggering X must trigger Y, or vice versa, right? So, but then, in order for this to happen, we have to understand what the individual elements are. And to understand them, let's go back to our favorite model, the brain. The basic unit in the brain is the neuron, which looks something like this. The neuron has a basic cell, the main body of the cell, the soma, which has the nucleus, and a bunch of connections, little tendrils going out called dendrites, through which you have incoming connections. Signals from other neurons come into this neuron through those dendrites. If the cumulative signal coming in from other neurons exceeds a threshold, then the neuron sort of trips and it fires. And this information goes down this long connection called the axon. And there's only one axon per neuron. And then eventually connects out to a bunch of other neurons. So obviously the most important part of the neuron is the axon. You snip it, the neuron is not doing anything. So the axon is actually protected by a little sheath of fat called the myelin sheath, which is actually formed of something called glial cells. And so here's something really magical. Your head is mostly fat. In fact, the more fat there is in your head, the smarter you are. So if somebody calls you a fathead, say thank you, right? They actually stored Einstein's head, and people tried to figure out why he was smarter. Turns out he doesn't have more neurons than the average person. What he has is more fat in his head. He has more glial cells. So being called a fathead is a compliment. Here's something else that's really interesting. Neurons don't divide. They don't undergo cell division, which means whatever neurons you're born with in your brain, that's it. After that, maybe you get a small number of neurons, and you may have additional neurons being formed from neuronal stem cells very early in childhood, but beyond maybe 2 years of age, you're pretty much fixed. After that, the only thing that happens in your brain is that your neurons die, which is a good thing, and we'll see why. Okay, but anyway, so he had this little neuron. We need a computational model for it. The first team to come up with a decent computational model for this were these two guys, Warren McCulloch and Walter Pitts. One of them was a neurophysiologist. The other one was a homeless guy, a hobo, who wanted to be a logician. And I have both their pictures on the screen. Who wants to guess who's the homeless guy and who's the neurophysiologist? Anyone? Anyone want to take a guess? Yes? The one to the right is the homeless guy. No, he's Warren McCulloch. He was the neurophysiologist. He's chilling with some wine. The guy to the left, who went on to become a professor in MIT, is Walter Pitts. He was a homeless guy. He ran away from home at the age of 15 and ended up at McCulloch's door wanting to. He used to exchange mail with Bertrand Russell and other mathematicians. He was a homeless guy. He hadn't actually gone through formal schooling. But then McCulloch let him in, and they worked on modeling the brain. And when Pitts was 20 years old, he was a mathematical genius. They came up with this paper, which I cannot understand even today, which is what, 80 years later? But I think most people who read the paper cannot understand it. The take-home lesson from this little paper was the model they came up with, which said that a neuron can be modeled as something that's shown in the figure. A neuron has incoming synaptic connections, and if the total signal coming down these synaptic connections exceeds a threshold, the neuron will fire, unless, and they have a second kind of connection, which is the inhibitory synapse. If there's a signal on the red line, the inhibitory synapse, then regardless of what else comes in, the neuron will not fire. And just this very simple model they showed can actually compose all kinds of Boolean functions. So here, for example, if the figure to the top left, in every single neuron over here, the threshold is 2. So you have a signal coming in from 1, which connects to the second neuron through 2 synapses in the top left figure. So anytime 1 fires, a little later 2 fires, because the total incoming signal is 2. So this is a delay. The one to the top right, again, the threshold is 2. Each incoming signal is connected to the neuron by 2 synapses. So if either of the 2 signals fires, then the total incoming signal is 2. The neuron is going to fire. Which Boolean gate is that? It's an OR, right? What about the one to the bottom left? What is that? That's an AND. And what's your name? Krish. Okay. And what about, since you've begun answering questions, the bottom right, what is that?
That I would say is a bit clear. It's like 1 and not 2.
1 and not 2. Exactly, right? 2 cannot fire, but 1 must fire. So you see, you can actually compose fairly complex Boolean circuits using these basic units. They went overboard, though, McCulloch and Pitts. They made tall claims. They claimed that their nets should be able to compute a small class of functions, but that if you provide it a tape, it actually becomes equivalent to a Turing machine. They claimed it's Turing complete. And obviously it's not, because it's a very finite state machine. These were just claims. And they didn't actually prove any of these results. They just made claims, and they didn't actually provide a mechanism whereby a network of this kind could learn to perform specific operations. For that, we had to wait a few years for Donald Hebb. Now, Donald Hebb, turns out that people in those days tend to be pretty eclectic. So this guy, he's another crazy guy he was actually a Canadian. He started off being a novelist. Then he decided to become a hobo. Then he decided to become a farmer. Then he decided to become a school teacher. Then he gave it all up and decided to do a PhD in psychology, right? And he came up with this idea of Hebbian learning, which says when the axon of a cell A is near enough to excite a cell B, and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells firing B is increased. Now, it's a very complex way of saying that if a neuron A repeatedly excites a neuron B, then the connection between A and B will be strengthened. He also said it very succinctly, saying neurons that fire together wire together. It's a beautiful way of saying it. So how does that work? So here's what the connection between neurons, how a typical synapse looks like. The neuron that's connecting to a second one has at the end of its axonal connection this little bulb, and that bulb connects to the synapse of the second neuron. It doesn't really connect, they don't touch. They have chemicals flowing between the two. And if neuron Xi repeatedly triggers neuron Y, then the synaptic knob gets larger, and so this connection gets stronger. Now you can actually which means that it becomes easier for X to trigger Y. You can think of this as the weight of a connection between X and Y. And it actually gives you a nice little formula. It says that anytime X and Y both fire, the connection gets stronger. So you can say the weight, every time X and Y fire together, the weight increases a little. I can write in math, I can say W equals W plus eta times XY. Now, XY is going to be 1 only if both X and Y are 1, which means both of them fire together. Now, there's a problem with this learning mechanism. Can anybody tell me what the problem is? Yeah. The connections only strengthen, right? They keep getting stronger and stronger. Nothing ever weakens. So it's an unstable learning mechanism. Eventually, what's your name? You'll have to write it down for me. So there's no notion of competition. Eventually, the whole brain is going to saturate, right? Now, there were other modifications later on which tried to account for the fact that this process is fundamentally unstable, like the so-called generalized Hebbian learning rule by Sanger, which allows for multiple outputs and so on. The point is, the basic Hebbian rule itself, while it's a very nice idea and it will keep making its appearance again and again over the course, in its raw form, it's not very good. So to improve this and come up with a real formal model which actually, with nice mathematical properties, we had to wait a few more years. For this guy, whose name we've seen already. This is the guy who came up with this big quote, which the New Yorker summarized very nicely, right? Frank Rosenblatt. He was, like all of them, a psychologist and a logician. He also came up with the number 42. In other words, he came up with a solution to everything in the universe. He came up with the perceptron. So what is the perceptron? It's a model for the neuron. And it actually sort of embodies what we saw about the cell. It also includes some of the aspects of what Donald Hebb proposed. So he says that within any cell, a cell has a number of inputs. Each input has a weight associated with it. So the total input that the neuron gets is going to be the weighted sum of all of its input. Each input is multiplied by its weight. All of them combined, you're going to get a weighted sum. If this weighted sum exceeds a threshold, the neuron will fire. So mathematically, you can say y equals 1 if the weighted sum of inputs exceeds a threshold. So summation wi xi is greater than t, or summation wi xi minus t is greater than 0, right? Or greater than or equal to 0, depending on how you do it. Otherwise, it doesn't fire. So it's a very nice, simple model. And he was really excited by it. He figured this little unit could perform any kind of computation. And he managed to convince the world. So the Navy actually pitched a whole lot of money into him, and the newspapers went overboard. This was from 1958. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Or the Oklahoma Times, Frankenstein monster designed by Navy, the Navy that thinks. There's this little circuit down here, right? Obviously, it's kind of an overstatement, and we'll see why. Now, what Rosenblatt did, along with coming up with this model, is he even came up with a learning mechanism, which said that if I want this unit to learn a specific function, then I can keep providing it examples of input-output pairs, and anytime the output is not what I want it to be. Again, mind you, this is a Boolean output, right? It either fires or it doesn't. Anytime the output is not what I want it to be, then I can scale the weights by the difference between what the output must be and what the output really is. This is the famous perceptron learning rule. And we will see this again in a few classes. So we basically update the weights whenever the perceptron output is wrong. He proved mathematically that this will actually converge, and if the classes can be represented, if a Boolean function can be represented by this unit, then it will actually learn, it will converge to the correct solution. And obviously, this can model Boolean Gates. So in these figures, the number inside the circle is a threshold. The number on top of each line is the weight of a connection. So the connection to the top left Now I'm using greater than or equal to for my logic. So the connection to the figure to the top left, that neuron obviously is only going to fire if both x and y fire. Then the total input is 2, which matches the threshold, it's going to fire. If one of them is 0, it's not going to fire, right? So that's an and. The one to the bottom, the threshold is 1. It's going to fire. The total input is going to be 1 if either of the two inputs is 1. So that's an OR. The one to the right, the weight is now -1. Observe that the weight is allowed to be negative. So if the input is 0, the total input is 0, the threshold is 0, it's going to fire. But if the input is 1, the total input is -1. The threshold is 0, it's not going to be fired, not going to fire. This is a NOT gate, right? So clearly this can perform all kinds of Boolean functions. Unfortunately, this single unit doesn't solve everything. Not very long after Rosenblatt made his really tall claim that he has solved all of the world's problems, Minsky and Papert came up with this book, a chapter in a book, where they showed that they can't model the simple XOR. This unit, this threshold unit, cannot actually capture the XOR function. So it's not a universal computing unit. But then you can perform an XOR if you network them. So the individual elements are weak computational elements, but if you network them, then you can actually perform stronger computations. For the XOR, for example, if you connect them like so. So now, it's not a single unit that's performing the XOR. It's a combination of 3 units. The first unit to the top computes X or Y. The unit to the bottom computes not X or not Y. And then you AND the two, and the final output is going to be your XOR. Now, here we introduce a terminology. These units, the outputs of these units are not seen. What you're really seeing is the output of the final unit at the end. So the units in the middle are what we will call the hidden units or the hidden layer. The key point, again, points that we've introduced are the notion that networked units can perform powerful computations, and that these network units can have hidden elements whose outputs are not really seen. But then once you get to this, you realize you can compute pretty much any Boolean function. So this is what we call a multi-layer perceptron. You can add these guys up in layers. You can do ANDs, you can do ORs, you can do NOTs, you can do XORs. Guess what? You can do pretty much anything. So here, for example, is a little network which computes that hideous function on top that I won't even bother to read, but the network will compute it. So the summary of everything we've done so far, neural networks began as computational models for the brain. They are connectionist machines, which comprise connections of networks of neural units. The early model was the McCulloch and Pitts model, where neurons were Boolean threshold units. It models the brain as performing propositional logic, but has no learning rule. Hebb's learning rule Hebb actually came up with a learning rule, neurons that fire together, wire together, but his learning rule is unstable. And so then Rosenblatt's perceptron, which is a variant of the McCulloch and Pitts neuron, actually has a provably convergent learning rule, but it's not universal. But once you begin networking these units, you can actually compose arbitrary Boolean functions, pretty much any Boolean function at all. Questions? None? On Piazza? No. Yeah?
So why did it take so much time for them to figure out that XOR can't be computed by?
I think it depends on the presentation. So Rosenblatt, I think, came up with his model in 61. In 1968, you had Minsky and Papert's paper. With hindsight, 2020 hindsight, it must be obvious because we know exactly what this model does. You will see this in a few minutes. But back in the day when you just presented this threshold unit as a gate, and when I went to college, we learned about threshold units. It was astonishing to me the kinds of things a threshold unit could perform, because it was presented as, here is this magical threshold, here are these weights, there's high dimensional space, you can compute all kinds of functions. It kind of hides the fact of what really is going on, that it's just a linear threshold. So it wasn't immediately apparent. Anything else? Okay. So we've seen that these things can be connected together and can do all kinds of perform magical Boolean tasks, right? The problem is our brain is not Boolean. Our brain actually has real valued inputs. It has continuous valued inputs. And we make non-Boolean inferences and predictions. It's not a 1-0 inference or a 1-0 prediction, right? So if you want real inputs, the perceptron with real inputs is going to look something like this, where now the x1 through xn, the inputs are real valued. The weights are also real valued. You're going to have these real valued connections, and the neuron will fire if the weighted combination of these real inputs exceeds a threshold. Now, there's one way you can think of this somewhat differently. I can say summation wi xi is greater than or equal to t. That's a logic, right? I can also say summation wi xi minus t is greater than or equal to 0, which is the same logic, right? Or I can write this as summation wi xi plus b, some threshold function, which is working where theta of x equals 1 if x greater than or equal to 0, right? They're all the same statement. But once I begin writing it in this manner, you realize that you can modify the theta over here. And so that theta, for example, I could replace it by a sigmoid. And if I think of it as a sigmoid, the output, you can think of the output as the probability of firing rather than just a binary firing or not. But then you can also replace it with other generic functions. We will go over these later in the course. For now, for the next few minutes, let's stay with the threshold unit, because it's very easy to interpret what's really going on with threshold units, right? So let's go back to our perceptron. Our perceptron fires if the weighted sum of inputs exceeds a threshold. Now, what is the boundary between when it fires and when it doesn't fire? Anyone? What would the boundary be? Pardon me?
Linear bound.
No, but what is the actual formula, right? Summation xi wi xi equals t is the boundary. When summation wi xi becomes greater than t, it's going to fire. When it's less than t, it's not going to fire. So that's a hyperplane. That's the equation for a hyperplane. In 2 dimensions, that's going to be a line. So if I had 2-dimensional input, the actual function that you're going to get is something like this. This is the line, which is the boundary. To the left of the line, it's a 0. Then it's going to jump up. To the right of the line, it's going to be a 1. Left and right being, where you look at it from. But the network it's going to look like this function, right? So if you look at it from the top, you're going to get that figure to the top right. There's a line. On one side of it, it's 1. On the other side of it, it's 0. The moment you see this, you will know how you can model Boolean functions using this network, using this unit. How so? If the inputs are Boolean, if I have 2 inputs, the inputs are going to be 0, 0, 0, 1, 1, 1, or 1, 0, right? If my threshold unit, if the boundary, the hyperplane, the boundary which separates the 1 from the 0 falls in the region between the 0, 0 and the diagonal, what is that gate? The figure to the top left. Which Boolean gate is that? That's an OR. It fires when the only time it doesn't fire is when both inputs are 0, right? What about the one to the top, the one in the middle? What is that? That's an AND. Both of them have to be 1, otherwise it doesn't fire. But this is just your perceptron, right? The guy to the top, to the right is a NOT. Why can you not do an XOR? For an XOR, you would have to, you have these points. For an XOR, you would have to go up here. These would be 0. These would be 1. That's not feasible, right? That's why this cannot do an XOR. So anyway, once you figure that you can do this, you can get a linear boundary, magic happens. How does magic happen? 2 dimensions. I want a function that's going to give me a 1 if the input lies in the pentagon, but not otherwise. It's got to give me a 0 outside. How can I do this? Anybody? Yeah.
5 different functions I can add.
Exactly, right? So here's what I can do. I can have one neuron which captures this boundary. It's a 0 below the line, 1 above. The second one gets me this boundary. The third one gets me this boundary. The fourth one gets me this boundary. The fifth one gets me this boundary. If I add their outputs with a weight of 1 each, then their sum is going to be 5 inside the pentagon and something less than 5 outside. If I use a threshold of 5, what is the output going to be? Exactly a 1 inside the pentagon, exactly a 0 outside, right? Now I can do this, right? Here's a crazier function. I want a 1 inside one of the two pentagons, a 0 outside. Guess what? I'm going to have one subnet generating one pentagon, another subnet generating the other pentagon. The two outputs are going to be summed. I have a threshold of 1. It's going to fire, regardless of which pentagon it's in. But now this is a much crazier boundary, right? And if I can do this boundary, I can do these things, right? How would I do it? Anyone? How would I do a boundary like this? Someone? Yes. I don't need a lot of layers, right? I can do something much simpler. I have my crazy guy boundary. I can chop it up into little polygons. I can have one subnetwork for every polygon and then OR the lot. And I get a boundary that actually looks like a human being. I can do pretty much any boundary once I figure this out, right? And which means I can get even more complex decision boundaries. Now think of a standard classification problem. You have some high dimensional space. In this high dimensional space, you're trying to compute a decision boundary. But what is the decision boundary? It's some arbitrary outline. And you want a 1 inside this outline and a 0 outside. We just saw that you can model pretty much any boundary using this network, right? Which means the network can actually give you these kinds of functions. So the story so far, MLPs are connectionist computational models. Individual perceptrons are computational equivalents of neurons. The multi-layer perceptron is just a layered composition of many of these units. They can model Boolean functions, so where individual perceptrons act as Boolean gates and networks of perceptrons are Boolean functions. But they are Boolean machines in that they can represent Boolean functions over linear boundaries, and they can give you arbitrary decision boundaries, right? So they can be used to classify data, regardless of how complex the decision boundary itself is, because the network is capable of modeling it. Now, but what about continuous valued functions? Something like this. How do you actually use the same network structure to model a continuous valued function? For this example, I'm going to start off with something that we'll revisit these topics in the next lecture. But for this example, I'm going to start off with a function of one variable. So I want to compute f of x. X is a scalar. F of x is a scalar, right? Now, let me start off with this little basic network, which has two threshold units. One of them has a threshold of T1, the other has a threshold of T2. I sum the outputs of these units. So what happens? If T1 is lesser than T2, and the weights are 1 and -1 respectively, as the input starts, until it exceeds T1, the output stays 0. The moment it exceeds T1, the first neuron fires, but the second doesn't, so the output becomes 1. When it exceeds T2, the second neuron also fires. It cancels out the output of the first neuron. The output goes back to 0. So you get this nice little step function, right? Or this little pulse. That's enough. Now you give me the arbitrary function. I can put a whole pile of these guys underneath it, and I can model pretty much any scalar function to arbitrary precision using these guys, right? So continuing with our story, what we found is that multi-layer perceptrons are connectionist computational models. They are classification engines. They can identify classes in the data. What I didn't get over is that individual perceptrons are feature detectors. We will get to do this in a later class. But we can, the MLP can also model continuous valued functions. So there are some bullets over here, which I didn't think I'd have time to go over, but the slides are there, right? So questions? We've seen how versatile these things are at this point, right? What else can they do? So far, we've looked at things that go strictly left to right. You give it some input, it computes stuff. The outputs are fed to more units, which compute something. Those outputs are fed to more units, which compute something. It goes down. It's a linear computation. But then, Lawrence Kuby in 1930 actually showed that if you had units of this kind and you connected them in loops, then they actually give you memory, networks that will remember. Now, which means that if you have a network of this kind, you trigger it with a part of a memory, it can recover the entire memory. We're not going to get to this topic until much later in the course, but these are not just simple machines which can compute Boolean functions, classification boundaries, and real valued functions. They can even remember, right? They can represent probability distributions. They can represent probability distributions over integers. They can represent probability distributions over real inputs, over complex valued inputs. They can model a priori and a posteriori probabilities. All of these we will see in class. But the point is, the versatility of these models is pretty immense. And yet the basic unit is very simple. It's just a threshold unit or some modification of it, and you connect them up, right? So in AI, as far as we are concerned, the neural network is a function. What we've seen when we started the class, we said, here are all these boxes. Something goes in, something comes out. What is it that relates as something input something to an output something? It's just a function. What we've seen also is that these little networks of these threshold units, or even things that aren't necessarily thresholds, can model functions. They can model almost any function at all, right? So a network is just a function. Given an input, it computes the function layer-wise to predict an output. More generally, given one or more inputs, it predicts one or more outputs. So over here, these tasks, the tasks that we began the class with, they're just functions, right? Every one of these is a function. An image goes in, a caption comes out. What is that? That's a function. A voice signal goes in, a transcription comes out. What is that? That's just a function. A game state goes in, a prediction for what move to make comes out. That is also just a function. So in fact, the way we model all of these are just functions. We are going to model every one of these things with a neural network, which will take in some input, some appropriate representation of the input, and give you an appropriate representation of the output from which you can perform downstream tasks. And so, our story so far, I'm coming to an end. This is my second to last slide. MLPs are connectionist computational models. They are classification engines. They can also model continuous valued functions. And most interesting AI tasks are functions that can be modeled by a network. So in the next class, which is on Friday, we will continue on the same vein. We will talk about networks as functions. We will talk about the limitations of networks when they try to model functions. And we are speaking of deep learning, right? So where does this notion of deep come in, and why is it important? We will also cover that topic. Questions?